Let's do some science experiments. I've got 2 flasks on a stir plates. We're going to add a little bit of water to both. Deionized water, well, distilled water. See if you get a little vortex going here. Let's see how that looks. Oh, that looks nice. Get a little bit more water over here on this side. There we go. Okay. How you doing there, Phoenix? We're going to do some science experiments. See what we get going on here. All right, let's add some universal indicator to both of these. Universal indicator is also known as rainbow indicator. It displays these colors at different pH values. So we can see what color the water turns when I add the universal indicator. Let's see what happens here. You can see it's red. Excuse me, it's red. Oh, nice, Kion. It's green, which tells me, the universal indicator is neutral. It's neither acidic nor basic. But check out what happens when I add it to the purified water. It starts off looking like it's green. But as it continues to interact with the water, we see it develops a yellow color, indicating that it is slightly acidic. And I'm used to that. I mean, it is surprising to some people to see that distilled or deionized water is slightly acidic. But that's very common. It's known by chemists. Any water that's exposed to the atmosphere is going to have carbon dioxide dissolved in it. And when carbon dioxide dissolves in water, it makes the water slightly acidic. Let's go ahead and add, again, the green universal indicator to this flask over here on the right. You'll notice the material I'm adding, it stays concentrated in the center of the vortex. And that makes sense if you recognize that, the center of the vortex is a low pressure region, and material tends to stay focused in low pressure regions. Material moves from low to high pressure. So if it's already in a low pressure zone, it's going to stay there. Okay, here we go. Let's add another squirt here of the universal indicator. This one I'm going to add out on the sides. And again, you can see that the universal indicator added to distilled water is yellow, indicating it is slightly acidic. And again, that's from the carbon dioxide that's in the atmosphere that dissolves in the water. Now what we're going to do is we're going to add either acid or base to these mixtures. And we're going to watch what happens. So we go over here on the right. Let's add 2 drops of sodium hydroxide base. You can see me adding it up here at the top. There's the first drop. There's the second. You can see the blue material grow through and change it to a violet color, indicating pH 10, very high pH. Over here on this side, we're going to add some acid, hydrochloric acid, the same acid that's found in your stomach. We're going to do 2 drops over here on the right. 1, 2. That red color you see in the center of the vortex tells us that, indeed, I've added some acid. And look at that, the whole thing's turning red. So yeah, in this flask, we've got a highly acidic mixture. Over here on the left, on the right, we have a highly acidic mixture. Over here on the left, we have a highly basic mixture. Now, I'm going to go ahead and try to neutralize this base. I'm going to do that by adding drops of acid. So over here on the left, let's add 1 drop of acid. See what happens. If you look carefully, you can just see a little bit of red color develop there down the center of the vortex. And it looks like the base completely consumes the acid that's been added. I'm going to add another drop here. You can see the red in the center, and as that red acid, thank you there, Morgan, as the red acid moves out into the surrounding fluid, the base will react with it. And it looks like there's plenty of base still, so I'm going to add another drop of acid, trying to see if I can neutralize the base. Let's see here. There it goes. Come on now. What's going on down there at the bottom? All right, maybe. I don't think, yep, I think it's still enough base to neutralize the acid. Let's add another drop of acid. You can see a bunch of red there growing. And we have neutralized the base. I've added enough acid. Well, no, not quite. It looks like we're around pH 8 maybe. So I've added enough acid to bring the pH from 10 down to 8. Let's add another drop of the acid. See what happens here. So the reaction that's happening is the reaction between sodium hydroxide and hydrochloric acid. The question is, what's causing this to happen? This is the chemical reaction that's happening. The sodium hydroxide, which was making this violet, reacts with hydrochloric acid to form salt and water. These are neutral. That's acidic. This is basic. Now over here, we have an excess of acid, which is why our pH is 3. Let's see what happens if I add a drop of base now. So right now in both of these flasks, I have an excess of hydrochloric acid, and that's why we've got a red color. I'm going to go ahead and add to this flask over here on the left that has an excess of hydrochloric acid. I'm going to add a drop of sodium hydroxide. So here it goes over here on the left. You can see me watching it at the top, and it goes. And we'll see if I've added enough base to neutralize the acid. That's right, Patrick. That is correct. The indicator here, the indicator system, matches the colors of the rainbow from low pH at 3, very acidic, to high pH at 10, violet, very basic. So in this case, I not only added enough base to neutralize the acid, but now there's also an excess of base. I'm going to try the same thing over here on the right-hand side. Let's add a drop of base over here on the right-hand side, see what happens. So in it goes. You can see it added. And I don't know what's going on here. Yeah, Morgan, we're looking at the pH scale. That's right. Sorry, I missed that comment a little while back. You can see the base I've added stays concentrated in the center, and that makes sense because just like the center of a hurricane, I have a hurricane's low pressure. The center of this vortex is low pressure, and material tends to stay in low pressure regions. You know, material moves from high pressure to low pressure. Looks like all of the base I added was neutralized. Let's add another drop. I'm going to add another drop of base over here. You can see me adding up right up here at the top. Add another drop of base. And let's see if the acid that's present is enough to neutralize it. I think the base is going to overpower it. You can see that violet color growing in. Sure enough, we have two very violet systems, very high pH. Let's start adding some acid to pull the pH back in the other direction. Kanalski wants it blue. I'll do my best. I'll do my best, Brando. I'll do my best. Here we go. So notice we both, in both systems now we're at pH 10, very high pH. All right, so I'm going to now start adding hydrochloric acid. That's the same acid that's found in your stomach. I'm going to go ahead and add one drop over here. Here it goes. Boop, and it goes, and we'll do the same one over here. We're going to add one drop over there on the left-hand side. We can try that, Phoenix. Phoenix says, what if I add the same amount of acid and base? Looks like we got a little rainbow going over here on the right, which is kind of cool. As the mixture attempts to homogenize and the acid and base react with each other, you'll often see the case where you'll get a variety of colors all in the same flask. I love that effect. It's very beautiful. I want to get a little more color over here on this side, so I'm going to add a little more indicator. Hello, Darius. Thanks for saying hi from Poland. I'm over here in the United States. Here we go. Let's add another big squirt of the universal indicator over there on the left. Try to get a little more color in, make it look a little prettier. All right. So yeah, right, we got, what color we got over there? We got like a pH 4 over there, 4 or 5 on the left-hand side, and maybe a pH of 6 over here on the right. Let's add another drop of acid over here on the right. And we're going to do a drop of base over here on the left. And it goes. I got you a flash of green. Here, let's add a bunch of acid over here on the left. Here we go. Drops of acid, 1. It's like the daylight breaking through the dark violet of night. Hey, someone from Africa. How you doing there, Daniel? Let's add another drop of acid over here on the left. Say the base I'm using is 20% by weight hydrochloric acid. Oh, Randall, you can do this in your science class. Very easy to set up. All I have is two different indicators. Two different flasks filled with water and universal indicator. And then I just add 20% by weight hydrochloric acid or 20% by weight sodium hydroxide. Over here on the left, let's add a drop up here. 20% sodium hydroxide. Boop, in it goes. Get a little rainbow effect going on. Hello there, Sebixon. We're going to do a drop over here on the right. You can see it. Here's the drop going in. 1 drop of sodium hydroxide on the right. Tornadoes, why are they different sizes? Let me make them a lighter color. I'm going to go ahead and add acid over here on the left so we can see down into the... Oh, look at those gorgeous colors, y'all. Those are pretty. Someone from India, hello. Hello, Cricket. Okay, so somebody asked why the tornadoes are different sizes. Let me turn the stir bar off and turn this one off. This one's a little bigger. You'll notice this stir bar is a little bigger than this one. They're basically the same size, though. So let's go ahead and turn them both to the same speed, which is halfway. Let's see. I think this one's a little bigger. I think the stir bar is a little bigger. Thank you there, Zed. Someone from Brazil, man. Thank you there, Locke. I'm loving the rainbow, too. So the different sizes of the stir bars generate different sizes of tornadoes, as does the different speeds at which I allow them to run. So this is kind of fun to do. I'm going to place this flask here in the middle. And now what I'm going to do is I'm going to draw some solution from both sides. And we're going to stick them there in that middle flask. All right? So if you've been paying attention, you should know what color this will make. Where's my... Excuse me a second. I got to get my... new droppers here. Oh! Here we go. Okay. So because acids and bases neutralize each other... Here we go. Let's pull a little bit of red from this side, a little bit of violet from this side, and we're going to add them both to this container here, and I'll keep doing this for a while. So I'm adding some solution that is acidic and basic to this middle flask. The acid is the red-colored mixture on the left. The base is the blue-colored mixture on the right. And you can see, as I'm squirting them in there, what we're basically ending up with is, it looks like, a yellow-green colored solution. See that? And that makes sense if you know what's going on with acidity and basicity. That is, this stuff over here has a pH of 3. This stuff over here has a pH of 9 or 10. And when you mix acids and bases together, they neutralize each other. So the pH is going to come closer to 7. And you can see this looks maybe like a pH of 6 or 7 when I mix the two together. So that is expected. Okay, let's leave this here so you can see the colors. I'm going to go ahead now and add a little bit of base over here on the left. Uh-oh, where'd I put my dropper? Here it is. A little bit of base. Here you go. 1 drop of base over here on the left. In it goes. And look how rapidly that changed this to a very high pH. Jess, if something appears red, orange, or yellow, it is acidic. If something is green, it is neutral. And if something is aqua, blue, or violet, it's basic. The further the pH number gets from 7, the more acidic or basic it is. So that's the way it works. Okay, let's add some acid over here on the right-hand side. You can see me adding it right up here at the top. In goes a drop. And we're going to add 2 drops over here on the left. 1, 2. You're welcome, Jess. Ha Kanalski, what we would have to do to test the acidity or basicity of urine with this indicator, of course, is we'd add this indicator to urine. All right, let's add some drops of base to each. One drop on the right, one drop on the left. Let's see if we can get the rainbow going. Jacob, the indicators I am using is a mixture of indicators. Together, they're known as universal indicator because they show the universal colors of the rainbow. But the actual indicators in my recipe of universal indicator is thymol blue, methyl red, bromothymol blue, and phenolphthalein, all in the same system. Jess, so water that has no color, we could test that. We would have to add the universal indicator. Universal indicator is a bunch of dyes. So we would add the, system of dyes, all of the dyes, to the water. And usually when I do that, it turns the water yellow because water has carbon dioxide in it if it's exposed to the air. And so carbon dioxide makes water slightly acidic. Ethan, I am using 20% by weight hydrochloric acid as my acid. So that is the same acid that's found in your stomach, except it's a lot more concentrated than what's found in your stomach. Ismail, what I'm doing is I have two different flasks with either, well, they both have water and they both have universal indicator in them. And then all I'm doing is I'm adding either acid or base. Yes, IP Blade, the solutions are quite concentrated. 20% by weight hydrochloric acid is indeed quite concentrated, which is why the colors are changing so fast. Okay, here we go. Let's add a drop of base over here on the right, base over here on the left. See what's going on. I'm going to turn the speed down just a bit. Let's add some acid here and see what happens. If you turn the speed down, the colors, the mixture of colors will persist for a while. Ethan, nice, very nice. Why do you like citric acid and why do you like hydrochloric so much? What is the concentration in moles per cubic decimeter of HCl? Oh boy. Let's see if I can do that approximation here real quick. So let's see. That's going to be, oh crap. I think it's 3 molar, but I'm not sure. I think it's 3 molar hydrochloric acid. Let me just try to, so it's going to be 20 grams of hydrochloric acid for every 100 grams of solution. The solution is going to be about 1.2 grams per mil, 1,000 mils per liter, and 36 grams per mole. So, Ismail, here's going to be your concentration. So let's see, that's going to be 200 times 1.2 divided by 36. I don't know what that comes out to, but that's going to be your concentration if my math is correct here that I'm doing quite quickly. So if you keep adding base to both of them, they keep changing colors without the final stage. I apologize, I don't understand the question. I will keep adding base to both, and if there's a drop of base to both right now. Zach, oh, that was gorgeous. We got a little rainbow flash over here. In order for it to go back to colorless, I would have to take the dyes out. So, Cammie, I'm going to continue to add base to both sides. And you're going to see it's going to continue to shift to a more and more violet color. Now, once it reaches pH 10 and pH 10 and higher, the system remains violet. So this particular system can only indicate different pHs from 3 to 10. At pH 10 and higher, it will remain violet, and at pH 3 and lower, it will remain red. I agree there, Sally. Ethan likes citric acid because of its presence in citrus fruits, indeed. and likes hydrochloric acid because the name sounds cool. Very, very nice. All right, let's add some acid to both, 1 drop each. Let's see what happens. If you look closer, you can see the red thread running through the middle there. What is pH 10 and pH 3? Ask Zek. pH 10 and pH 3, I'm not 100% sure what you're asking, Zek, but what it refers to is the concentration of protons that are present in the solution. So the way we chemists think about acidity is with this ion here. We call it the H plus ion. It's a hydrogen atom that has lost an electron. And the more of this that's in the solution, the more basic it is. The less of this that's in the solution, the more basic it gets. And the more basic it gets, the more hydroxide ion there is in solution. That's the way that kind of works. All right? Let's throw this up here. Let's see if get this one going here. You can see the colors there. Yeah, that one works. Well, my other one's getting a little old. How can you calculate the proton and neutron found in both those liquids? Well, Zach, we're not going to be able to find the neutron concentration. The proton concentration, that's just the H plus ion concentration. And indeed, when you put H plus ions into solution, these molecules that are in here, the different dye molecules, what they do is they grab onto, so to speak, chemically, those protons. So, for example, there happens to be one particular molecule in this system. Now, remember, there's 4, and I'm just going to talk about one of the molecules. One of the molecules in here is called phenolphthalein, and phenolphthalein can have 2 different structures. One of the structures is ring-shaped like this, and we're going to represent the H plus ion by this white piece of plastic. So if phenolphthalein binds to a proton, it has a ring shape, and it's colorless. So when there's a lot of acid around, there's a lot of protons around, so phenolphthalein molecules, they all grab onto that, and they all take on this ring shape, and with this ring shape is the molecule is colorless. Now, if there's a lot of bases around, and that means there's not much protons around, and there's also molecules, bases are molecules that steal these things. So if you're in a heavily basic system, these protons will be stolen from the phenolphthalein, and when that happens, the phenolphthalein molecule goes pop like that, it pops open, and with that change in structure comes a change in color from colorless to pink. And that's the way the phenolphthalein molecule works. And the other molecules in here work in a similar way. They're just going to have different colors that they generate based on how many protons they have. Why you have one spinning faster than the other? Cammy, just for the heck of it. So long, Sally. Christy tried to adjust the pH of a fish tank once, and the buffers kept bringing it back to neutral, and then it crashed. Ah, okay. So, yeah, what a buffer is a system. Here, let's just show you. Let's make a buffer, all right? Let's make a buffer. So before I make the buffer, just check this out. We're going to make a buffer here, okay? So notice I'm adding acid to this flask over here, and I'm going to add acid to this flask over here. And notice what happens to the colors when I add acid. They change, which means the pH is changing. All right? So that's what's going on. I'm going to add a little bit of base over here, 1 drop over there on the right. And you can see that color change from pH 3 to pH 10 with 1 quick drop of base. Now I'll go over here and I'm going to add like 3 drops of acid. And if I add that 3 drops of acid, we have gone from a pH of 10 back down to a pH of 3. Now what I'm going to do over here in this flask is I'm going to create a buffer. And the way I'm going to create the buffer is very simply by adding an Alka-Seltzer tablet to this. And what the Alka-Seltzer tablet will ultimately do, it's going to make it so that in this system, there will both be an acid capable of reacting with any added base and a base that's capable of reacting with any added acid. So the Alka-Seltzer tablet's going through over here. You can see it's producing a lot of carbon dioxide. Those are the bubbles that are being produced. And notice our pH is 6. And this, I'm very used to seeing this when I put Alka-Seltzer tablet in the system. What happens is the system gets buffered, we say, to pH 6. And what that means is that this is going to resist changes in pH because this contains both an acid that will react with any base that I add, and it also contains a base that will react with any acid that I add. Here, let me show you here. Let's add this. First, I'm going to add base, okay? And notice up here, I do like to do this because up here you're going to see a bunch of bubbles. Those are carbon dioxide bubbles, and carbon dioxide bubbles react with sodium hydroxide. So here we go. I'm going to add sodium hydroxide, and as I add it, look what happens to those bubbles. They start to disappear as the sodium hydroxide reacts with the carbon dioxide acid that's present in here. But notice, I added a crap ton of sodium hydroxide, and the pH is still basically 6. That's because this system is buffered. Over here, if I do the same thing, I'm going to add a drop of sodium hydroxide over here on this side. I just added 1 drop, and watch what happens. We're at pH 3 over here, and I added 1 drop of base. We got the rainbow effect, which I love, and we went from pH 3 to pH 7. I'm going to add a second drop of base. Remember, I added 3 over here, 3 or 4. So 2 drops of base got me from pH 3 to pH 10 in the unbuffered system. Let's add like, I don't know, 3 more drops. Watch it up here. I'm going to do it. 1, 2, 3 drops to the buffered system. And with those 3 drops, we're pretty much still pH 6. Now, what do you mean by a buffer crashing? What that would mean is if I add enough base to this that it reacts away all the acid that is in here, then the buffer will no longer stay at pH 6 and start to move toward basic. That's what happened to your fish tank system. All right, so let's add a little acid over here on the right. In goes 2 drops. And we're going to add a little acid over here on the left. 2 drops. And in the unbuffered system, which is over here, we went from pH 10 to pH 6 with 2 drops. And in the buffered system, we stayed at pH 6. Why is one tornado bigger than the other if they're both in water? That's going to come by different stir speeds, and these are the stir bars are different sizes. Here, I'll turn this one up. So I'm going to turn this side up. Right down here, you can see me turning up the speed. Watch what happens as I turn up the speed of the stir bar. The tornado gets larger. And over here, I'll turn this one up now. I'm going to turn this one up here. As I turn this one up, you can see the vortex gets larger. Oh, it's just starting to go. There it goes. Thank you there, Teddy. Thanks for hanging out. I appreciate that. All right, let's start adding a bunch of acid over here on the right. Very cool. And I'm going to add a drop of base over here on the right. In goes 1 drop. And we got a flash of rainbow, baby. Come on, I love that. Come on, I love that. All right, 1 more drop. That should get us back to pH 10. RDBT, I'm using 20% by weight hydrochloric acid as my acid. Here, I'll add a bunch of drops there. And I'm adding 20% by weight sodium hydroxide as my base. Neon, most people would say, is it safe to drink at 7, which is neutral? And the answer there is, well, yes, if it didn't have the indicator system to it. The problem with drinking it with the indicator system is one of the indicators is a laxative. You got it, Zane. Why don't I use 100% concentration of hydrochloric acid? Because I like to, I don't want the fumes, man. That's nasty stuff. I do not want the fumes. Indeed, gaming gamer. Bases can be just as scary as acids. Indeed. So yeah, I'm adding a bunch. Look at this. I'm adding a bunch of acid. I'm dropping in like crazy over here on the left. In the buffered system, nothing's happening. All right, let's add a drop of base over here on the right. Boop, and it goes. Give me the rainbow. Come on, there it is. I'm loving the rainbow, the flash of rainbow. How you doing there, Malcolm? Thank you there. It looks like Cloudy Dreams, I'm guessing is the name. You got it. What the heck is this? Let me tell you what it is. In these flasks, I have some water, and to the water, I've added a universal pH indicator. Well, what is a universal pH indicator? It's just a mixture of dyes. But what's interesting about this mixture of dyes is it changes color depending upon pH. And pH is just how acidic or basic something is. You can see the pH scale right here that I've got it listed right here. So you can see the different colors that you might see in the flask. So right now we see in this flask, the pH is 10, which means it's very basic. And if I add acid to this system, here, up here at the top, you can see me do it right here. I'm going to add 3 drops of acid, 1, 2, 3. And when I add those 3 drops of acid, the color changes. And that's because the acid neutralizes the base and brought us to a pH just below 7. So it looks like I have a little excess of acid. Let me add 2 more drops of acid over here. There they go. And now I've changed it from a pH 6 to maybe a pH 4 and 5. 2 more drops of acid, boom, boom, and they go. And now I've moved from a pH of 4 down to a pH of 3. By buffered, I mean resist changes in pH. So there we go. I'm going to show you what buffered means here in a second. I'm going to go ahead and add 2 drops of base over here. There's 1. I'm adding it to the right. There's the second drop of base. And notice, in 2 drops of base, of course, we got the rainbow, which is gorgeous. In 2 drops of base, we went from pH 3 to pH 7, okay? Now, let's check out the buffered system. That's this system over here. This is my buffered system, which is at pH 6. I'm going to add the same base over here, 2 drops, 1, 2, and we're still at yellow. Here, let's add 2 drops of base over here. Ready? 1, 2. This is the unbuffered system. 2 drops took me from 7 to 10, just like that. Yes, Ethan, there are levels below pH 3. Unfortunately, my pH system, my indicator system, will only show red at pH 3 and below. It will also only show violet at pH 10 and above. Eden, the yellow one won't change because it is buffered. I've got both an acid and a base present in here that resist changes in pH. I'm adding a bunch of base right now to the buffered system. And I'm seeing I may have, let's see, maybe I've added enough base to get it off of pH 6, but I'm not sure. Great question. Somebody asked, what would happen if I mixed red and purple water? Let me show you. It's a great question. Great question. We're going to do that right now, all right? If you've been watching, you know what's going to happen if I mix red and purple water. Here we go. I'll show you right here. All right. So I'm going to take some fluid from this, which is blue. So then goes 1, 2, 3, 4, 5 squirts from the violet, okay? Now let's make it red. I'm going to make it red by adding acid. Here's my hydrochloric acid. It's the same acid that's found in your stomach. In it goes. You can see the pH is going to go from 10 at a violet color to red, which is pH 3. Come on, baby. Get it red. There we go. I think that's red enough. What do you think? Okay, now remember, we took all that purple stuff, right? And now we're going to add some of this red stuff. If you've been following along, you should know what color we're going to get. Here we go. Add some red. 1, 2, 3, 4, and I think we're there. It took 4. There you go. So they neutralize each other, right? So I took, here, let me show you. I took some fluid at pH 3, and I took some fluid at pH 10. I mixed them together, and they neutralized each other. They gave me a green fluid. Great question. And that's a fun experiment to do. Fun experiment to do. What other questions? Let's see what else. Can I make it I thought it would make it yellow. Neon Foxy, that'd be a great guess. That could have happened. Yep, you got it, Neon. Green is neutral. How does the base and acid make it change color? Sunset, it's complicated because there are actually 4 different dyes, okay? There are 4 different dyes in this system. However, we can focus on this one right here because it's simple. Phenolphthalene's in here, and phenolphthalein, it helps make the violet color because blue and red make violet. So phenolphthalein shows 2 colors. It's going to be either colorless or it's going to be pink. And here's the way it works. When there's a lot of acid around, here, let's do this while I'm jabbering on, okay? So at least you got something to look at while I'm talking theory, okay? I'm going to slow that down. I'm going to add a lot of base over here, and we're just going to see what happens to this side, all right? Who knows what's going to happen? Maybe I'll chase it with a little acid. All right, what's going to happen over there? Anyway, phenolphthalein works like this. It's a ring-shaped molecule, and it grabs onto something that we call a proton. Acids donate protons. So when there's a lot of acid around, the phenolphthalein molecule finds one of these protons, and it grabs onto it, and it has a ring-like structure. And when it's ring-like structure like this, it's colorless. Now, when bases are around, that means there's not much protons around, and the bases actually steal protons. So the bases come along and they steal the proton, and when that happens to phenolphthalein, it undergoes a structural change from ring-like to pop. It pops open like that. So it goes like this in an acid, boop, to that in a base. And with that change in structure, an acid to base, comes a change in color. This form of phenolphthalein is pink. This form of phenolphthalein is colorless. And that's how it works with one of the indicator dyes that's present in this system. We're getting a little bit of beauty over here, and that's kind of cool. Let me add a little bit of acid over here to try to make this a little lighter. And I'm going to get this off of here because the buffered system is really kind of boring. I mean, once you see it once, it's like, okay, we got the color, we got it. Nothing's changing over there in the buffered system. Let's make another one. Here, we can do this here. I can show you exactly how I set this experiment up. So we're going to go ahead and we're going to put an empty flask over here. That's correct, Francesco. So it's just a proportion between open and closed forms of many different molecules in the system. And I can't remember. I don't think all the molecules in the system are sort of this ring-shaped structural change. But they all undergo a structural change, on whether they're in an acid or base. Okay, so here we go. We're going to show you how this starts. All right, I'm going to turn on the stir bar. There you go. So we got the stir bar going. And then we're going to add to this some water. So just get it going in there. Oh, looks like I knocked the stir bar out of orbit. Let me get that stir bar going again. Turn her off. Get her going. Notice that's a really small stir bar there. It's a tiny one. There we go. Got her moving. And now I'm going to add the universal indicator. Thank you there, Emma. Appreciate that. Let's add a little bit of the universal indicator here. All right. So the universal indicator you'll see is green, which means it's neutral. Watch what happens when I add it to the water. And that's distilled water, by the way, folks, which is purified water. What the heck? It turns yellow. That means the water is slightly acidic. Here, let me show you the colors just so you remember here. So yeah, the pH indicator is neutral at start, but then I stick it in the water and it goes yellow, which is acidic. What the heck is going on there? Well, any water that is in contact with the atmosphere will have carbon dioxide dissolved in it, and carbon dioxide is an acid. So as the carbon dioxide dissolves into the water, it makes it quite acidic. Come on there, a bunch of Brazil flags. Welcome. I hope everything's going all right. All right, now that I've added this, I've got the indicator system ready. We're going to go ahead and add some drops of hydrochloric acid, 2 drops. 1, 2. Get some gorgeous patterns going on. So yeah, 2 drops of acid is all it took. And we are at pH 3, which is quite acidic, yeah? Okay, now I'm going to try the other thing. I'm going to add base. Let's add 1 drop of base. Let's see if 1 drop of base will neutralize the acid. If so, 1 drop of base will turn us to a yellow color. Let's see. 1 drop of base, and it goes. Somebody's asking about blood being acidic or basic buffer. Blood pH is 7.4. It's buffered to pH 7.4. That's correct, Francesco, and that is not a dumb question. Fizzy water is definitely more acidic than flat water because you bubble carbon dioxide into water to make it fizzy or to make it carbonated. All about that base. I love it. How are H3O plus and hydroxide present in the solution? IB Blade. The structure of acid and hydronium in solution, that's complex. I mean, there's a lot of theory that goes on with that. Um, I mean, basically, there are some molecules of water that take on a proton, and so there is some H3O plus in water. And hydroxide's the same way. There's just, the way I envision it is there's just a bunch of those ions floating around in the water. There we go. At what pH levels does it start to become hazardous? Anime, that's a nice question. You know, I would say that, the dangerousness of an acid has more to do with the chemical nature of the acid than it does whether the acid is acidic or not. So, for example, there are some acids that we need to survive, like ascorbic acid. Ascorbic acid is better known as vitamin C. And we drink, we drink acids at like pH 2, soda water, orange juice. I can get down there like pH 2 or 3. So I would say, though, if you're just thinking strictly about pH, once you start getting down around pH 1, I wouldn't think that'd be so good for you. I like this one a little better because the colors tend to persist with the smaller stir bar. It's unable to mix things as quickly. If I keep adding those acid and base drops, will the water container eventually break? No, it won't. I mean, the acid that I'm adding is benign enough, and it doesn't react with the glass. So hydrochloric acid does not react with glass. Sodium hydroxide does react with glass, but the concentrations that I'm adding are so low that it's not gonna affect the glass. I've been doing this for years. So long, Neon. Thanks for joining in. Ismail, is that no problem or Neptunium? Liquid oxygen or liquid chlorine more dangerous? I would avoid liquid chlorine more than liquid oxygen. Thank you there, Mateo. I appreciate that. Thank you there, Emma. You got it, Zachy. I don't know if you're talking to me. I agree there, God's Neko. Let's add some acid to both sides. 3 drops. 1, 2, 3. Let's see what happens. You can see that nice red thread. Thank you there, Tony. Appreciate the sub. All right, Ismail. Couple drops. Do protons kind of act like electrons in solution? I would say no. I would say emphatically no. Those are going to act very different in solution. Nice, Cody, chemist. The biochemist has entered the chat. Cody breaking out the positive effects of acids. You need them. You need them. What will happen if you combine carbon dioxide and aluminum? Simone or Simon? In my understanding, carbon dioxide does not react with aluminum, but correct me if my chemistry is mistaken, anybody. Mohammed, what we are seeing is universal indicator in some water. And then I'm either adding acid or base so we can watch some color changes. That's it. Thank you there, H. Ward. And so it's just, we're talking about science, but we're also just kind of, in my opinion, enjoying some of the beauty of just nature. Earlier, the glass on the left was buffered. How did I buffer it? Dominic, all I did is I added a Alka-Seltzer tablet to it, and that's going to add a citric acid buffer to the system. I think it's if I remember correctly. Oh, I have to sit and think about it. I think it's I think I want to be careful, but I think it's hydrogen citrate, dihydrogen citrate buffer. Nice, Zachy. That's right, IP Blade. Aluminum does already have a very unreacted oxide layer. What I'm wondering, IP, is if you breach that oxide layer, for example, by adding chloride ion, that oxide layer can be breached. So, I guess that's my question. If you put some aluminum in a solution with an enormous amount of dissolved carbon dioxide, and then you add chloride ion to breach that oxide layer, will that react with carbon dioxide? I'm thinking no. I don't think it'll do it, but, I could be wrong. Ah, there you go. Ismail, bringing in some of the chemistry that should make sense at high temperature. CO2 may be able to react with aluminum. I'm a little skeptical of that, though, because, usually compounds tend to break down at higher temperatures. So I would imagine aluminum carbonate would break down into aluminum oxide and carbon dioxide at higher temperatures. But I don't know. Can I tell about the most rare lab chemical I own? Yeah. Yugi, I don't know if this is the most rare, but it's one of the most interesting, Yugi. Y'all go to my channel and check out the short on the freakiest chemical reaction. So I use some Gallinstan, and I show it's an alloy. It's an alloy of gallium, indium, and tin, and I show how that reacts with copper ions, and what happens is just remarkable. So Yugi, check it out. If I added chlorine ions in water, would the chlorine ions bind to the protons in water? So chloride ions, no. So chloride ions do not react with protons because hydrochloric acid is a strong acid. These are not redox reactions, Muhammad. They are acid-base reactions. I'm trying to get back through some of the comments. So long, Zachy. Yeah, the Venom one, Tony. You saw it. Come on, baby. I'm loving it. Here, let's add some. Oh, that's cool. That's cool to hear. Some people are doing some after-school care, checking this out. That's awesome. I love doing science for kids. Why is there a purple stripe on the left container? Here, let me show you. Let's do the purple stripe, okay? Here we go, IP. Okay, what I'm going to do, IP, is notice these are both red, so the pH is very low. I'm now going to add base. And the base, is pH 10. That's gonna look violet. And what happens is just like this vortex here, I'm adding the base. So just like the eye of a hurricane is low pressure, the center of this vortex is low pressure, and material doesn't leave low pressure systems. Material moves from high pressure to low pressure. So this low pressure system, the base that I've added, it's pretty much going to stay there. Oh, L Boy Willie, how and why does it change color? I'm going to answer this in a simple way. Okay, this takes a little bit of theory. It's more complicated than this because there are actually 4 different dyes in these systems. And I'm just going to talk about one of them because it's the simplest way to talk about it. All right, let's turn this off and let's add a bunch of acid here. And let's just kind of see what happens here if I add it. And we're just going to watch the magic happen, okay, while I talk about this. So how does it change color? Look at that. We got a little rainbow going on over here. So one of the molecules in here is called phenolphthalein, and phenolphthalein has a ring-like structure in an acid. Man, that's gorgeous. That is really pretty. Now, we're going to imagine that this is a proton, and acids donate protons. So when there's a lot of acid around, the phenolphthalein molecule, which is represented by my fingers, grabs onto this proton, and when it does that, it gains a ring-like structure. When phenolphthalein has a ring-like structure, it's colorless. Now, in a base, these protons get taken away because bases are proton acceptors. So there's a lot of base around. the protons get stolen from the phenolphthalein molecule. And when that happens, the structure of the phenolphthalein molecule goes bink like that. It goes from a ring structure to an open structure. And with that change in structure comes a change in color. From colorless in acid, boop, to pink in base. That's the way it works. Thank you there, Croesus. All right, I think at some point I'm gonna be ending the live here, and just so you know, what I do at the end of the live is I flip the camera around and I let you see my ugly mug, and we talk for a little bit, just about whatever you want to talk about. Oh, that's pretty. God, is that pretty? So yeah, just know that's coming. Thank you there, Suave. You're welcome, L Boy Willie. Thank you there, Yugi. Hey, so yeah, I'll be talking to you. So, you know, the live is going to be coming to the end, but I'll flip it around. We'll talk like 5-10 minutes is what we do, and just say hi to you. You can see my face. Some people want to see that. I don't know why. I'm warning you though. It's not something you're going to want to see. All right, you're going to be looking at an old man, an old man in his basement, just letting you know, with reading glasses on, so I can see whatever the heck is being written on the on my phone. Good luck there, Tony. I don't wish you luck. I wish you a clear mind is what I wish. Here, let's turn this on. I wonder if this will turn green as they'll neutralize each other. Let's find out. Oh, I think we had a little more base. Yep. Let's try this one over here. Probably more base as well. Thank you there, Windscar. Appreciate it. All right, let's flip this around here. Talk to you for a bit if you want to hang out. There we go. Thanks for hanging out tonight, folks. What's up there, Chong Chang? Hey there, Croesus. Thank you there, Tony. Hello there, Muhammad. I sound older than I look. Well, thanks there, Serial, I guess. I'm doing okay. You got it, Zane. You got it, IP Blade. You're welcome. pH level shows the concentration of protons in solution. It's actually the power of 10 of the hydrogen ion concentration. Levi, I am a physical chemist. Yeah, I know now, Red. I think he's great, man. I think he does a lot of cool stuff. Oh, yeah, Cody, I do these about once a week. What did I use as a neutral? I apologize. I don't understand the question, God's neck. What is electronegativity? Ismail, I wish, Nerfetti. Doggone it, I don't have grandkids yet. How'd I get into chemistry? What's electronegativity? Lots of questions here. I agree, Minecraft man. Appreciate that, brub. What does a physical chemist do? Devin, they do a lot of different things. I can tell you what this physical chemist does. I'm a chemistry teacher. I also do research and design of new science and chemistry experiments, and I try to share them with the public, and I just try to share, in my view, what is the beauty of science. You know, just everyday stuff. If you just pay attention, man. I mean, if you just pay attention, it's like the whole thing is magic. The whole universe is just like really cool. And it's just fun to share that with people. The oxide layer from aluminum. I don't know if you can move it mechanically by scratching LOC. I just stick it in some a solution of chloride ions. Thank you there, Anime. I teach at the college level. I went to school at a state school in Pennsylvania, and then I got a master's degree at a school in North Carolina, and then I got my PhD at the University of Michigan. Go blue, baby! Brilliant astrobiology and astrophysics here. What's your take on 5D composites? Levi, I apologize. I don't know what that means. Teach me. I have no idea. Yeah, IP. pH characterizes the solution's potential to give hydrogen. H+. H+. Do I think graphene battery is the future? I don't know enough about it to be able to comment. I do know that folks are starting to replace the lithium in batteries with sodium, which is a good, a good thing to be looking into. So long, Ismail. Thanks for hanging out. Thanks, there, Rodriguez. Most people do hate Atkins' physical chemistry, Mohammed. Sodium chloride battery. I'm not so sure that's going to work real well. There you go, Morbid. Michigan. Hello there, Rod. Nice, Jaihoon. Cool, man. Oh, I love it, Robert. That is so cool. Do I have a video on different colored fire? I do, Devin. You're gonna have to scroll back pretty far. I did that like 2 or 3 years ago. That's correct. Pawn Sock Gaming. A proton is just a hydrogen atom that has an electron removed. Because, a hydrogen atom, they're mostly just a proton with a singular electron. You take that off, you just got the proton there. Interesting. Yeah, that's correct, Robert. They definitely need to get rid of the cobalt. Yes. Nice wick, BDI. Very cool, anime. Thank you there, Rod Doof. Consider the position, space, spin orientation, topological direction, and imposition, superimposition of spinors within doped materials. What kind of spinors are we talking about? We sometimes use spinors to describe, if I remember correctly, the frequency of just the atomic orbitals. So I'm not sure how you're using the term spinor there. Sorry, Jaihoon. I apologize. I don't know how. Hey, thanks there, Daniel. Gallon stand is crazy, isn't it? It's fun, man. It's absolutely fun. Does chemistry anyhow consider more deep atom levels that protons, electrons, and neutrons? So here's the deal, IP Blade. When I was a kid, I'd say in high school, chemistry was the study of matter. That's what they called it. And then, as time went on, in my opinion, the particle physicists stole that from us. So, if you go deeper than the atom, you're still looking at matter, right? You're looking at quarks and all the stuff that matter's made of. But that somehow got cordoned off into the realm of physics. It's just the way that we decided to characterize it. So I think chemistry is nowadays defined as the chemistry of materials or the chemistry of the atoms in the periodic table. Thank you there, Jahun. Hello there, fellow. Jihoon, got it. Kevin, deuterium nuclei behave similarly to protium nuclei with respect to pH. They're a little different, just a little bit different. That extra neutron in there is going to make things behave a little differently. I got to remember this. I think, so if we had like DCl versus HCl, I think the hydrogen, the H plus, leaves the chloride ion a little easier than the deuteron, the D plus. And so, essentially it's the same, but that extra mass in that deuteron, it just tweaks things a little bit. That's cool, Gozneko. Thoughts on them taking ether of the periodic table? I apologize. I don't understand the question. To answer the question about physically removing an oxide, you can, but it reforms almost instantly. Okay, so as you scrub the aluminum, the oxide layer forms almost instantly. Very cool. Yes, fellow, have you tasted D2O? They say it tastes sweeter. I've not tried it. I don't know who that is among Red. Educate me. Let's mess around. Okay, here we go. Anything material has 3 axes in space, X, Y, Z, in higher dimensions. Oh, in higher dimensions. Anything material has 3 axes in space, even in higher dimensions, I think you're saying. You consider superposition within de Sitter and anti-de Sitter space, chiral consideration, and photon potential within the, and I apologize, I don't know what de Sitter and anti-de Sitter space is. I apologize, I have no idea what that is. Plans for the rest of the day? I'm gonna maybe make a little dinner and watch some NFL football. Oh, Nahi, I'm sorry you're struggling. I would suggest you just get a tutor, someone that you really resonate with who can, help you with this material. Aha, won't be doing that among Red. Yeah, Rodriguez, I do it about once a week. I understand, Levi. I wish we could have the question. I wish I'd be able to talk to you. So my son, he's getting a PhD in physics, and he calls me all the time and telling me about the stuff he's doing. And man, it takes. I'm a physical chemist, so I can understand a lot of what he's talking about. But we just sometimes, we're on the phone and he's telling me something. I just can't get it, man. I just can't get it. And but sometimes when he visits, I can get a little deeper. But usually I do okay. So long, fellow. All right, folks, I'm taking off. Thanks for hanging out and checking out some of the beauty of science with me. It sure does, Zane. Uh, and hey, happy birthday, Charlotte. And you all have a great day tomorrow and a great evening tonight. And be sure to check out the beauty of the universe and nature and the earth that's all around you. It's so easy to see, man. Just pay attention and look at things a little closely. Be a stranger to the ordinary. You can do that.